All right, let's get into it. When you think of concrete, you probably just picture sidewalks, maybe some construction sites. Kind of boring, right? Well, what if I told you that gray stuff holding our entire world together is actually in the middle of a quiet, high tech revolution? We're talking about a whole new recipe that could change what durable even means. See, for all its strength, traditional concrete has a hidden vulnerability. It's this tiny weakness that lets the environment attack our buildings and bridges from the inside out, causing them to crack and crumble, sometimes way, way earlier than they were ever designed to. So in this explainer, we're going to break it all down. We'll start with concrete's big problem, then we'll look at the first attempted fix, uncover the chemical secret behind a game-changing new formula, see what it actually means out in the real world, and then we'll take a little peek at what's coming next. Okay, so first things first, let's get to the heart of it, the concrete conundrum. I mean, why does this stuff that seems as solid as a rock need saving in the first place? Well, the secret is that concrete isn't truly solid. If you could zoom way in, down to the microscopic level, you'd see it's actually a whole network of pores and tiny little tunnels. And while those are necessary for it to form, they also end up acting like superhighways for destructive chemicals to just march right in and wreak havoc. And there are two main bad guys leading the charge. For any structure that's near the ocean or in a place that gets icy, you've got a chloride attack from salts. These little ions sneak in, they find the steel rebar inside, and they start rusting it out. That makes the steel expand and crack the concrete from the inside. The other big threat is carbonation. That's just CO2 from the air, slowly seeping in and zapping concrete's natural chemical shield, leaving that same steel rebar totally exposed and defenseless. Now, of course, engineers knew about all this, and their first attempt to fight back was pretty clever, but it led them straight into this frustrating dead end that they called the durability dilemma. The idea was to recycle industrial waste, things like fly ash from power plants and slag from making steel. You mix these into the cement, and it makes the concrete's internal structure way denser, basically putting up roadblocks on those chemical highways. It seemed like the perfect win-win for durability and for the environment. But the data told a different story. And this chart really lays out that frustrating trade-off. See that first bar? The chloride resistance is awesome with these additives, right? But then look at the second bar. The carbonation resistance just plummets. It's actually worse than plain old concrete, which you can see over there in the third bar. And this quote just nails the problem. By adding those materials, you are using up the very stuff that gives concrete its natural rust-protecting shield. So, yeah, you could protect against one threat, but only by throwing the doors wide open for the other one. Engineers basically had to pick their poison. They couldn't beat both at the same time. But that whole dilemma is what makes this next breakthrough so brilliant. The solution wasn't about finding one single perfect ingredient. It was about getting two really common materials to work together in a completely new way. It's called limestone calcined clay cement, or just LC3 for short. And yet, it's a three-part blend, but the magic isn't just about mixing things together. It's about sparking a chemical synergy that solves that old dilemma and creates something way stronger than any of the parts could be on their own. So here's how this chemical team-up works. You've got key ingredients from the clay and the limestone. They actually lock together and form these brand new, super dense crystals that are basically custom-built to clog up all those destructive highways inside the concrete. They also help stabilize other space-filling structures, making the entire internal network incredibly dense. What do you get? A fortress-like internal shield. So this is the secret sauce, right here. The limestone stops being just a simple, passive fill material and becomes an active chemical player in the game. That synergy is what lets LC3 create this incredibly dense and refined pore structure, something far beyond what fly ash or slag could ever do by themselves. And all this clever chemistry, it isn't just for a textbook. It translates into real-world benefits that make this new concrete recipe stronger, greener, and a whole lot smarter. So one of the biggest wins here is that you don't need some high-purity, expensive clay for this to work. LC3 can be made with lower-grade clays, the kind of stuff that's often just left behind at mines as waste. All of a sudden, a material people were throwing away becomes a key ingredient in high-performance concrete. We're talking upcycling on a massive scale. And just look at the performance. That chloride shield is just off the charts. Now, yeah, you can see the carbonation shield is still lower than plain cement, but check out the other metrics. The pore structure becomes incredibly fine, and it does it fast. And look at this last one, curing sensitivity. Curing is just keeping the concrete moist while it hardens. The old additives were really finicky. If you didn't cure them perfectly on a windy, hot job site, you'd lose a ton of the benefits. But LC3 is tough, it's robust. It gets to that high performance without all the extra babysitting, which means the strength you design in the lab is the strength you actually get in the real world. But here it is. Here's the killer stat. LC3 concrete can be more than 10 times more electrically resistive. You can think of corrosion as a tiny destructive battery. It needs an electrical current to flow. By making the concrete 10 times less conductive, you're essentially just taking the juice out of that battery, slowing down all of those chemical attacks to a crawl. So LC3 is a massive leap forward, no doubt about it. But the innovation doesn't stop here. Scientists are already exploring the next frontier, really pushing the boundaries of what our building materials can even be. They're looking at everything. I'm talking about agricultural waste, like ash from sugarcane that's packed with useful stuff, all the way to entirely new chemistries. Imagine binders called geopolymers that don't use any traditional cement at all. Instead of just adding water, you activate them with special chemical solutions, creating materials with just incredible resistance to fire and acid. And that leaves us with a pretty fascinating question for the future, doesn't it? We've just seen how a smarter recipe can revolutionize the world's most common material. But the next great leap, it might not be a recipe at all, but a complete reinvention of the very ingredients we use to build our world.